Okay, so welcome back, and today we're going to start talking about another classical approach to calculus, okay? And this is what we call the area problem, okay? So we've talked about the tangent problem, the problem of the tangent line. We've also talked about velocity, and now we're going to talk about the problem area, the area with problem. Or excuse me, the problem with area. Okay, so now, in many different fields, physics, business, probability, all deal with trying to find the area under a curve. Okay? And so that begs the question, how do you find the area between a curve and the x-axis? So what we're going to do is we're going to approach this the same way that we approached the other problems, the idea of approximating, right? So we're going to simplify things in order to approximate what the area would be. So what would be the simplest thing we could do? Well, the simplest thing we could do is use rectangles. Okay, it's easy to find the area of a rectangle, base times height. So what we're going to do is, to help approximate the area under this curve, what we're going to do is we're going to take the interval from A to B. So we have this interval from A to B. We want to find the area under this curve. To approximate it, what we're going to do is we're going to subdivide this interval from A to B into smaller intervals. And we're going to do something like this. We're going to subdivide it into smaller subintervals and create rectangles. Right? And let's say we want equal rectangles. We want our rectangles to be the same. That'll make it easier for us to calculate, right? Okay, so okay, something like that. So what we could do is we can have these subintervals. Let's call this x1, x2, x3, all the way to what? X of k. Right? And so we've got these subintervals, and since we're dealing with rectangles, we can calculate the area of each one of these rectangles, and we can approximate the area under the curve from A to B by summing up the area of each of the rectangles. Now, also, what happens if we do more subintervals? What if we, instead of this many, what if we do more subintervals? Well, the more subintervals we have, the smaller the width becomes, right? And the more accurate the sum of these rectangles become. Which brings us to the idea of taking a limit again. So we're going to take the limit as the number of subintervals gets larger. Okay, we're going to talk about limits in the next section. But what we're doing is we're saying, hey, if we increase the number of subintervals, our rectangles will become more and more, well, how do I say this? The rectangles, the areas of those rectangles will be closer, and as we sum up those areas, we'll get closer and closer to the real area, because as you notice, some of these rectangles, pieces of the rectangles are above the line, some of them are below the line, so our estimate is not going to be exact, but as our rectangles become thinner, we're going to be able to get a more accurate approximation, and that's where we're heading. Okay, so this is kind of begs the question of what we're talking about before. is we're going to end up talking about limits. Okay, so what happens to this sum as we increase the number of rectangles we have? More rectangles means a better approximation. So now, what if we had something like this? Okay, what if we had something like this function, f of x equals x squared plus 1, and we want to approximate it using 3 rectangles, okay? And the way we're going to do is we're just going to use units. So let's say we have this. And, well, yeah, actually, you know what, let me redo this. Let me redo this way. Okay, so let's say we have that. Now, we want to approximate the area under this curve from 1 to 3. And so what we're going to do is we're going to use these rectangles to do it. And each rectangle has a height of so many units. Okay, so again, if we look at this, and again, we're going to get more technical with this, but just to bring the point home, we're going to deal with something very simple. We're just going to deal with square units. So if we want to approximate this area here, then we would just add up the areas of these square units. And so the approximation for this one would be, how many square units do we have? We have 1, 2, 3, 4, 5, 6 square units. Okay? And so the area under the curve, we would approximate it as 6 units squared. Okay? And so that's the idea. So again, once we get into the nitty-gritty and we start, in the next section we're going to start talking about limits, how to take a limit. This is going to be more, become more clear. We're going to be able to be more precise, and we'll be able to be more, what's the word I'm looking for? We're going to be able to bring a more algebraic look at this and to bring calculus, so that way we can get an exact answer, not our approximation. So this is called integral calculus. This is part of one of the types of calculus you're going to use. So the other type, when we're talking about looking at the tangent line, finding the slope, right? That is what we call differential calculus, okay? Or dealing with derivatives, what we call a derivative. Here, we're going to talk about integrals, and this is what we call part of integral calculus. And this is actually the setup of what we're going to talk about later, which is called a definite integral. Okay, but that's going to be later on. Okay, that's it. Have a great day.